So next speaker of this session is Dr. Arunima Banerjee from Physics Department of IISER Tirupati. Arunima completed her integrated PhD from Indian Institute of Science, Bangalore. Her research interest lies in the area of theoretical astrophysics, and particularly she is looking at the dynamics of galaxies using high resolution n-body hydrodynamical stimulation and machine learning. Today she will be talking on identifying lopsidedness in spiral galaxies.
Thank you, Balraman, and thank you, Anil. Since most of the ancient Indian astronomers were also mathematicians, so Dr. Anil has aptly set the stage for a galaxies talk now. So today I'll be focusing on the automated classification of two different types of spiral galaxies, namely grand design and flocculent spiral galaxies, using a very classic machine learning model which is very much well used for image classification studies, namely convolutional neural network. So what you see in the backdrop, which might not be visible given the lights here, is a picture of our Milky Way on a clear night sky. So our local habitat in the local group of galaxies is the Milky Way or the Akash Ganga, or the galaxy with a capital G, which given our vantage point on the galactic plane appears like an edge-on galaxy to us. So it is also a prototypical spiral galaxy, a prototypical grand design spiral galaxies. Two different types of spiral galaxies I'll be talking about today. One is grand design and the other is flocculent. It is a but as I said, given our vantage point, we are not in a position to see the magnificent spiral arms sported by the Milky Way galaxy. We have indirect observational means supporting the presence of spiral arms in the Milky Way galaxy. So this work was led by Dr. Shuman Sarkar, who was a postdoctoral fellow in our group, and collaborated with Ganesh Narayanan and myself and Prem Prakash, who was a project assistant. Prem Prakash was a project assistant in our group. Ganesh Narayanan was a PhD student. And it was done some time back in 2023. And I'll be focusing on this work and also tell you about some recent related work. So I give you the plan of the talk over here, again trying to motivate with a picture of the Andromeda or the M31. So on a clear night sky with sufficient exposure, this is how our neighboring spiral galaxy Andromeda or the M31 looks like from the solar system or from the Earth. So this is the plan of the talk. I'll give you a brief introduction on what galaxies are, and focusing on these galaxies. I'll then move on to the theory of formation of spiral arms, the majestic, the magnificent spiral features which you are used to seeing in galaxy images. What is the theory behind the formation of those structures, and what are the open challenges we face in galaxy formation theory these days? I'll follow it up with a brief introduction on deep convolutional neural networks, or DCENN, the classic machine learning model which is used for automating classification of images. So if I give you a bunch of images of spiral galaxies, when I say bunch of, I mean of the order of 20 or 30,000. Out of that, you can pick up and tell me these are the grand design spirals, these are the flocculent spirals, and these are neither in this group. So that is the type of objective we have for this work, because given the new facilities coming up like VLT, Euclid, the large international facilities or the optical telescopes, we will be getting galaxy images of the orders of tens of thousands. So it would be a humongous task to look at each of these galaxies and find out what is the structural feature of that galaxy. So anyway, we are looking at a small subset of that problem today in this talk. If I give you pictures of spiral galaxies, can you tell me whether it is a grand design spiral or a flocculent spiral, and so on? I'll then move on to the core of the talk, which is our work, and that is application of DCNN to classify these two types of spiral galaxies, and also tell you about some ongoing projects in the group, and wind up with the summary. So what are galaxies? So let me start with this classic picture of Hubble's morphological classification of galaxies. So what you see on the left are the elliptical galaxies, the galaxies with elliptical morphology driven by the physics of the system. So these galaxies are supported against the gravitational collapse by their random motion or the pressure support. On the other hand, on the right, you see the disk galaxies, the focus of today's talk, which, as the name suggests, sport a disky morphology driven by angular momentum support. Our Milky Way is a disk galaxy, and if you look at the disk galaxies, most of them sport spiral arms. Okay? These are the spiral arms. Right. So if your viewpoint with respect to any external galaxy is such that the symmetry axis of the galaxy is in the plane of the sky. So the galaxy, the stellar disk of the galaxy has a symmetry axis. So if the symmetry axis is in the plane of the sky, that galaxy is at an edge-on orientation with respect to you. And as I said, the Milky Way is at an edge-on orientation with respect to us, and as a result, we don't see the beautiful features present on the plane of the Milky Way. On the other hand, if a galaxy is at a face-on orientation with respect to us, for example here, that means the symmetry axis of the galaxy is perpendicular to the plane of the sky. Here the plane of the sky is the plane of the board, and as a result, you see all the beautiful features in the plane of the galaxy. So in today's talk, I'll be focusing on these type of external galaxies such that image classification based on the presence of spiral arms is possible. Right. So this is my one slide primer of the basic building blocks for disk type galaxy, okay, most of which sport spiral arms. Again, I am showing an edge-on view of disk type galaxies. So this galaxy is composed of stars and gas constrained in a thin plane which is hosted in a gigantic dark matter halo. And as I said, disk galaxies are pressure supported in the plane, the disk galaxies are rotation supported in the plane, that is the gravitational collapse is counterbalanced by the angular momentum support, and perpendicular to the plane there pressure or random motion supported. Okay. And the most important feature of this galaxy is its differential rotation. So unlike a solid body, this galaxy does not have a constant angular speed as a function of radius. Okay. The angular velocity of a disk galaxy falls off with radius, and this feature is known as differential rotation. Differential rotation is crucial in the formation of spiral arms of disk galaxies, as I will briefly mention in the next slides. Now, let's focus on galactic spiral arms. So what you see here is a multi-observatory view of M74, a classic grand design spiral galaxy. So when I say grand design spiral arms, I mean they have very well delineated spiral structure present in their galactic plane. Now what you see the three images of the same galaxy over here. The extreme left one is an HST image, that is the Hubble Space Telescope image. Of course, it is an optical image. All of these talks, throughout this talk, I'll be talking about stars and hence optical or infrared images only. Okay. The second image is the image of the same galaxy, which is the combination of the optical as well as JWST, James Webb Space Telescope image, which is an infrared telescope recently come up, and you can very well make out the nitty-gritty features, the nitty-gritties of the galaxies coming up better in the infrared, because infrared sees through dust. And on the extreme right, you have the infrared or the James Webb telescope image, which again shows out, how the fine features of the galaxies are now visible to us given the next generation telescopes or the new facilities. So that gives us the motivation to automate our methods of classification of galaxies, so that we can constrain our galaxy formation models better, because we have now tighter constraints for our models, so our models should be much more well developed. Okay, and right, so that was mostly about grand design galaxies. Now you see, definitely there is a spiral arm over here, but the appearance of the spiral arm over here is much different than that of the grand design spiral. Here it is more like fluffy flocculents. So these kind of spiral arms are known as the flocculent spiral arms. So I will try to develop a machine learning model to distinguish between these two types of spiral arms in this talk. Right. Now, these are not only beautiful or aesthetically pleasing features in the galaxies, they are the driving factors of galaxy evolution. So as you can well make out, there is, the spiral arms are non-axisymmetric features in the galaxies, and as a result, they exert torques and are instrumental in angular momentum transport, and hence the galactic evolution as a whole. They are also, being the overdense regions in the galaxies, the primary sites of star formation. Okay, now why they are theoretically interesting? So as we can make out, as I mentioned, a galactic disk is differentially rotating. So if you visualize the galactic disk as a combination of concentric rings, each ring is rotating with a different angular velocity. That is what shear is. So the innermost ring is rotating faster compared to the outermost rings. So as a result, if you draw with paint at t equal to time 1 a line on the galactic disk, it will slowly get wound up with time. So this is time 2, time 3, and so on. So this shows that the galaxy is rotating in a clockwise direction, and the inner rings are rotating faster than those of the outer rings. And as a result, had our spiral arms being only a material arm, okay, they would have wound up. So that right away tells us the spiral arms of the galaxies cannot be material arms. So Lin and Xu in 1964 proposed their model of the galactic spiral arm being a density wave which rotates with a patterned speed. That means it is not a solid, it is not a solid body, but it is rotating with a patterned speed. So it is like a ceiling fan, but it is not a solid body like the ceiling fan. It is rotating like a ceiling fan superimposed on the differentially rotating disk of the galaxy, but it is not a solid body. What it is a density wave. So how do I explain what a density wave is? I will just use the analogy of the traffic jam, which is routinely used in the textbooks of galactic dynamics. So suppose I am on a highway and there is a repair truck, the red one. The repair truck is slowly moving along the highway, and as a result it creates a bottleneck in the highway. So the cars approaching the repair truck from the left will slow down. Again, it will pick up speed after it bypasses the repair truck and move on. So if I am standing on the footpath, I will make out that different cars are coming, slowing down near the repair truck. The density is increasing over there. The density of cars is increasing near the repair truck. And then the car picks up speed, the cars pick up speed, and the density again becomes average, the average density. And slowly this over density moves on. But if I am on the aeroplane and looking at the city from a height, I will not be able to make out that at different points of time, the overdensity is being constituted by different cars. I'll just see an overdensity moving with the speed of the repair truck. So that is precisely what a density wave is. That is precisely what is happening in the galaxy when we see a spiral arm. Okay, but the model is elegant, beautiful, but there are open questions. Also, the flocculent galaxies are not very well studied. So there is a need to have a statistically large number of galaxies in high resolution, thanks to the new facilities we have these days, so that we can propose highly constrained models of spiral arm formation. So precisely there, the deep convolutional neural networks come in. So this is the structure of a deep convolutional neural network. So convolution, as the name suggests, is a kernel. So by trial and error, the network, the various layers of the network try to detect edges, textures, and features, different edges like vertical lines, horizontal lines, this, that. And by trial and error, it tries to build a model to find out which set of features constitute a grand design spiral and which set of features constitute a flocculent spiral. Okay? And the term deep relates to the number of layers you have in a network. When I say deep convolutional neural network, layers. The number of layers are usually of the order of 10 to 13 or so on. Yeah, here I just wanted to show you how a deep convolutional neural network, starting with the image of Vinayaka, does convolutions using different kernels, detects the edges, then does max pooling. Max pooling is nothing but downsizing, and then accentuates by the activation function to find out which are the basic features which will let you understand this is the image of Ganesha. Anyways, now our work was, as I said, based on this publicly available, very old architecture, AlexNet, deep convolutional neural network. These are all the inbuilt layers and parameters of AlexNet. We just used that, and we had to just tweak the hyperparameters, namely the learning rate, the decay rate. It is like like we do fitting exercise, fitting of the weights of the matrices, the kernels, the weights of the matrices, so that it gives me a model of the Ganesha. The different features, when combined together, will give me an idea that this is a Ganesha's image. Okay, so these were the technical parameters, and it is doable using a reasonable desktop. We don't need HPC, etc. for that. Okay, these were the feature maps from our study, just to give you a feel of the two different classes, right? And this is our loss function. This is like our chi-square when we do best fitting using linear best fitting model. So we are essentially at every epoch, which is every iteration, reducing this chi-square by changing the weights, right? So this is for monitoring how you are doing at every epoch. Is your loss decreasing or loss increasing, etc., etc. This is your training images, a subset of your my training images, flocculent and grand design. Okay, these are the performance matrices. At the end, you set aside 20% of your training images to see how your trained model, you train the model with also images, 80% of the images, but after that 20% of the images are set aside for testing how your model is doing, and that is given by the accuracy, that is the ratio of the correct predictions to the total predictions. Thus our model did very well, because we got a testing accuracy of about 95% or so on. This is a different work. Let me come to the testing accuracy part. It was 95% of testing accuracy. This is my confusion matrix. Anyways, after testing this model, we could predict 700 new grand design galaxies and 500 new lopsided galaxies. So these galaxy images were just available as spiral galaxies. They were not classified yet in the publicly available database, optical database, the Sloan Digital Sky Survey database. And from there we picked up those spiral galaxy images and did the classification and came up with new images. So thank you. I will end the talk. I will just flash the ongoing project. Very similar project, but working on two different types of galaxies, lopsided galaxies and symmetric galaxies. Thank you.
So thank you, Arunima, for your nice overview on dynamics of viral galaxies. The now session is open for question and answers.
Thanks for a nice talk. One hears about supermassive black holes at the center of galaxies. Can your machine learning tell you if there is one?
Yes, it can tell, but not this model. This is convolutional neural network. A black hole will, emit jets like AGNs and all. So if you have sets of galaxy images with central concentration of light and no central concentration of light, indirectly we can say these are the AGN candidates. Probably there is a supermassive black hole. From spectroscopy we can make out. So if you have a spectroscopy, not beautiful images, but just spectroscopy data, using random forest models, we can easily make out.
Thank you.
When you're using convolutional neural networks in order to recreate or classify these galaxies, how many images in training and how many images in test? And where you're taking these pictures, does it depend on your classification probabilities? Do they depend on
Yes.
where you're taking these pictures from?
Yeah, they depend. So I have to, if I want to predict SDSS images, I have to train using SDSS images. Otherwise, there will be issues. And I need of the order of a few hundred images. I mean, people say that is not enough, but we have seen several times, if you give me 200 images, it is more than enough. Raw images, no, 200 in each category. Okay, and as I said, it has to be, then you have to use that model for the prediction of images from that survey only.
Yeah, Arunima, very nice talk. Do you also get some information about their receding rates or their ages? All that also could be obtained from these models?
Their receding velocities and all those.
Yes, disappearing.
Not from convolutional neural network models. From spectra you can.
And about the age?
Age again, this spectra, metallicity, which metal emission lines are present, those will tell us. Color variation, those will tell us.
Thank you.
Yes, so thank you, Arunima.
Thank you.